Now, I'm Jonathan Fay. I'm Principal Architect for Microsoft WorldWide Telescope. And today I'm going to start out giving you a little bit of an overview about WorldWide Telescope. Some of this will be across the range of science, so where we started.
Is the switch on?
On the
It should be on. It's off. It's off.
Okay. Let's try this again. Okay. Good. You can all hear me. So WorldWide Telescope is something that was a convergence of some ideas that have been floating around from a lot of people. But essentially, Jim Gray had worked together with Alex Islay from the Johns Hopkins University, and they had basically come to this conclusion that in astronomy, and something that has also happened with a lot of other fields, that astronomy had gone from becoming an observation-centric science where astronomers would go up, they would observe their own data, they would collect it, correlate it, make some sort of a judgment on it, and come up with a theory, support the theory, and publish. It had gone from that sort of an environment to one where it was a data-centric environment. Everything was about data mining work that had already been done for the most part, and that really what the world needed was a worldwide telescope that was the World Wide Web connected up with all the astronomy data that had ever been collected, and that's where science would be heading with astronomy. But essentially, as this whole shift to the fourth paradigm of this data-intensive science, essentially almost all science is now connected with computer science, because without these computer systems, really a lot of the science work in basic science research wouldn't be able to happen. And so we started out with the field of astronomy because of Jim Gray's observation in this. And then Curtis Wong had this concept of essentially this storytelling engine that you could bring in. Essentially everybody who's got data has a story to tell with that data. And so he had this idea that there should be this engine that you could bring in data together with a story and be able to present a narrative that then people could appreciate the narrative, learn about it, and then from that narrative they could jump into the data and actually examine it with contextual exploration tools. And then from those tools, be able to come in and actually examine the data. And so if you have this concept of this interactive work that could contain the story behind it along with all the supporting data and the tools to be able to access that data. At about that time, I was also working on these tools for visualization that were based upon being able to explore a universe of data and large data, and being able to work with things like Earth and the sky and other planets and things like this. And this was several years before the explosion of popular tools like Google Earth and Virtual Earth, and really was kind of connected into what started me off was Jim Gray and Tom Barkley's work in the TerraServer project. And I wanted to basically figure out how we could help visualize some of that data in a pretty compelling way. And so we made a 3D Earth browser for TerraServer. That was pretty much kept inside Microsoft, and I developed it more towards the astronomy side of things, since that was my interest. So all of these tools kind of coming together, we decided to create a demonstration of this technology at a internal science fair called TechFest a few years ago. Unfortunately, about a month before the TechFest presentation, Jim tragically disappeared in a boating incident. And at that point, a lot of his technology with mapping and stuff was used to try to find him, but unfortunately no sign was ever seen of them. But one of the things is that in a memorial to him, Curtis and I decided that we had to basically not only do something that was a technical demonstration, but basically create something that was a gift to science and science outreach that would be able to have the tools that could be used by scientists to do this research and really see the fruition of his dream of this happen and get it out to the masses. Well, since that's happened, we started out with the target audience, which was like astronomers and earth science researchers. Then our secondary audience of educators and outreach, and then our third, which is like public and amateur astronomers and people who are interested in just looking at pretty eye candy of the universe. The focus, the actual audience members themselves are inversely and exponentially so. And so we have about over 5 million users, and of course there's about 10,000 professional astronomers on Earth. So it means that even though our priority is for research first, the audience itself is the public audience is definitely also coming in droves. We've created a lot of tools to make things very easy for our astronomy community, and in the last few years we've been working to try to also make these tools really applicable to what we do for our Earth research. And one of the things that we realized is that we had to solve some things that were not entirely unique to astronomy, but were especially important to astronomers. One of the things is that prior to WorldWide Telescope, they really hadn't dealt with a lot of global data sets. Individual images and studies of work were usually done on very small parts of the sky, and they really didn't assemble their data into large mosaics. And one of the reasons why is because most of the large mosaics had to have compromises in how they were displaying the data. So, for instance, you're all familiar with Mercator projection or equirectangular, and the types of limitations having a singularity at the pole that basically means that polar data is usually treated as a second-class citizen or not even allowed to come to the party at all. And a lot of the traditional GIS tools, basically, if you have a global mosaic, the poles are either severely distorted or not available at all. So for astronomers, the poles are really nothing special, but they're also just as special as any place else in the sky. When it comes to planetary scientists, the poles actually have a special spot because there's a lot of dynamics that happen. And in case of things like the Moon and Mars, looking at the polar caps is some place where they can look for resources, look for water or ice. So these are areas where there is a specific need to have additional types of data at the poles. So the other thing is that the best way to map a planet is to have a polar orbiting satellite. And by the nature of its orbit, it's going to select the polar data to be significantly more dense than any place else on the planet. And one of the things NASA found out a few years ago is when they exported to another one of their partners that was using equirectangular projection, is most of the data ended up falling in the region that tool couldn't display in any significant way. And so one of the things that we had to do for being a primary science-oriented product was to solve that. And so we worked together with other mapping researchers at Microsoft to create something called TOAST, or the Tessellated Octahedral Adaptive Subdivision Transform. And after saying that mouthful, you know why we call it TOAST. But what it does is it provides the ability to have pole-to-pole coverage and global coverage all at the same time without being anything special at the pole. So there's no, while there's some distortion across the area in the data storage in terms of it's not perfectly equal area, but there is no geographical consideration to having any area that has any more or less distortion than any other area. And the other aspect of it, it's designed from the get-go to be something that is projected into 3D space in the end. So while a lot of the other maps were selected from a GIS perspective because they like the ability to show the data without reprojecting it as a flat image. The TOAST format is never designed to be viewed directly like that, but always designed to be projected into an environment where you're actually corrected for whatever view you're doing. It also has the nice property of being adaptive in that you can look at planet scale data, and as you're zooming in on it, you can have data that's very far away at one level of detail and data that's close at a higher level of detail, and be able to adapt that grid that you're looking at it on the fly. Well, without further ado, I'm going to start up WorldWide Telescope and start showing you some of what that can do. So, WorldWide Telescope, yeah, let's kill some of the lights. Could we get I think all the lights would be good to start with here, and possibly the curtains as well if we can, so we can, it's a reasonably bright projector. So right here we're looking at the okay, so first thing I'm going to do is actually make sure my power supply is charging, because otherwise I will be out of battery. Okay, that appears to be working. It'll also help because when my battery is not charging, it turns off the graphics processor and uses the limp mode, which for graphics-oriented hardware isn't so fun. So this is our 3D space mode, which basically has the entire universe that we've collected data for in it. We have a Earth mode that we can see the Earth by itself. We have planet modes to look at the other planets, like Mars, for instance, here. And this basically lets us kind of operate in a solo mode where we have just a single focus at a time, as opposed to the universe mode, which we can navigate between different reference frames entirely continuously. And then we have our sky mode. And this is the original mode that was so interesting to astronomers. Give you an idea here, we can zoom into the California Nebula, and we're looking at data down to 1 arcsecond per pixel, or this is a 1 terapixel image, or 1 million by 1 million. As we zoom into it, you'll notice that it will progressively refine the data as we zoom in. So essentially, we've divided this terapixel up into a tiled multi-resolution image, and we're zooming into the area that we need to. I'll show you an example of going into the pole here. And as we're zooming into the pole, you notice there's nothing really special about the pole. Looks the same as anywhere else. The one thing you'll notice is that there's actually a trail here in red, and that artifact is actually caused by a polar orbiting satellite that happened to be going over the pole when this image was taken. So this ability to bring in data really, as we started showing this to astronomers, and showing them a functionality like our multi-wavelength sky. While this is a beautiful 1 terapixel panorama and the largest image of a single subject matter seamless mosaic that's ever been created, we also have lots of other wavelengths. And in astronomy and other data, in other science, you're not just interested in one map, you're interested in lots of different maps and what type of correlations they have between each other. And so, for instance, we can bring in this X-ray map. We also have everything from radio to microwave to dust, infrared, hydrogen alpha, and all the way up to gamma. So we can come in and take a look at this area, and then we can see this large extended X-ray structure. And then as we move back over to the visual, we can see that there's this correlation here between the edge of this extended X-ray structure that's actually happening in the visual. And so as you can see them both together, a scientist could then observe that this is actually a supernova shock front. And what's happening is you're seeing the extended X-ray energy, but you're also seeing as the shock front from that supernova is hitting this interstellar medium, that this nebula is being lit up by that. And so you can actually see what's called the Veil Nebula that's actually occurring here. And so this is something that, without being able to bring in these multi-wavelength and additional data, you really don't have the opportunity to see that much data in just a single band. So in WorldWide Telescope, we realized that as you're going to be doing viewing of data on Earth, being able to bring in different types of data sets and being able to switch between them and bringing in your own data sets and mapping them onto Earth is something that's going to be really important for being able to do research. And so we've tried to make it easy to both be able to get at access of a lot of data that's already been collected, as well as bringing in your own data from your own sources. And so one of the things we've experienced a lot of earthquakes recently, including Haiti and Chile and Japan and things like that. And as people are trying to visualize where these are all happening and what's going on, looking at a query from something like the National Earthquake Information Center to look at the earthquakes, you may be able to find out what the distributions are by looking at a chart or something like that. But to really try to scan through like a year's worth of earthquakes, like we have here, and make a lot of sense in it, just as a table isn't going to be very productive. And there's certain types of charts you can do, but the best way to visualize this, if you want to see some of the spatial and time correlations, is to be able to actually take this and plot it by space and time. So in WorldWide Telescope, we have these different reference frames. We start out with like the sun and then the planets, and so we can come in here and we have Earth and Moon and ISS. And these reference frames, we have stock reference frames that define a relative offset and location to another reference frame. But you can also put in your own. So if you have data that's located in a specific part of Earth or in an orbital reference frame, or like for a satellite or for a space probe mission or something, or a particular patch of ground. For instance, we've had data that has been basically staked out on a 100-meter grid or something, where someone has just had a bunch of data that's been cataloged by X and Y location on a particular grid. And if we can figure out the orientation of that grid and the latitude and longitude of one of the corners, we can actually then plot that into a global data set and integrate it with other types of data sets by basically merging in these various reference frames. And so we can change the do coordinate transforms to bring things into this universal view. So in this case here, I'm just going to plot this data on Earth. And we have a couple of ways of getting it in. You can do simple cut and paste, but we also have an Excel plugin that we're going to be showing in the tutorial in more depth this morning. I'll start out with a quick demonstration with just pasting. And we're going to go ahead and type in the layer name as Quakes. And as you go through the wizard, it basically allows you to select rows and the columns and how they're associated with the visualization data. We try to make an initial first guess to look for things like latitude and longitude, elevation, depth, altitude. And we try to make a judgment as to what sort of units they're being used in so that we can get pretty smart defaults when we start with. So in this case, it's picked latitude and longitude. Lat and long is the latitude and longitude columns. It's picked the depth column for the altitude, depth, distance type figure. And it's guessed that it's in kilometers, and that's correct. we're looking at the scale factor. In this case, it found a something called mag, which it assumed was a magnitude, and put it of a world coordinate scale with a power scale. And so I actually know that this data is probably going to look a little bit too big that way, so I'm going to put it down to about a quarter scale factor. I'm going to just use some Gaussians for plotting it. And for now, I'm just going to have a single color for everything. And this is going to also allow us to have date ranges. So we can pick start and end dates, columns, and we can also specify decays on this to be able to look at data that has a time component for it. It shows us, when we select our columns, it shows us the begin and end date range so that we can have an idea of what the range of these dates are. And then we can also have a hover text, so we can specify, well, maybe the time of the earthquake is a pretty good hover text, so we can figure out the time and date that that earthquake occurred. So now as we click Finish, it's plotted this data. Well, since earthquakes, I think red would make a little bit better color to make it pop out a little bit more. And now we can actually come in here and start viewing this data. And as you notice, this is actually viewing in 3D. So we can actually look from the latitude, longitude, and depth, and the magnitude. We can see where these dynamic heat maps that are generated with all the energy that was released by that earthquake. And we can also see the depth of this. So we can actually look at the effects of the subduction zone on the occurrences of this earthquake. And in fact, you can kind of have a first order representation of where the actual subduction zones are just by looking at the earthquake itself, the earthquakes themselves in the raw. So we can pop down here and do similar things looking down under the Andes, and you can see the subduction zone there. And by keeping this moving with motion parallax, you can get a really good 3D effect even without stereo glasses. So essentially, we can now want to support this data with other types of data that we might have available. So for instance, if we want to look at correlations between the earthquakes and fault lines, we can go ahead and pull in some data from earthquake faults here, and we can right-click on that and go ahead and color them yellow. And so we can bring that in there. We can also bring in things like the plate tectonic boundaries. We can shift between different versions of the Earth background. So, for instance, this is a summer or a winter image. We can bring in other types of things like SQL spatial geometry with the well-known text format, and so we can pull data in and let's go ahead and open a file in Excel here. Let's see, and go Recents and pull in some geometry and go ahead and select this geometry, and then go ahead and plot that by just pasting this layer in. And this has OGC well-known text, and which is basically an expression of geometry terms. And now we can have 3D geometry extruded. So this could be these are political areas, but they could also be like watersheds or looking at other data that's extruded or real 3D paths. And so as you can imagine, you can also bring in other types of image layers, and all of these can then be brought together and put together as tours. So for instance, if we want to take a time series look at what's actually going on in that earthquake data, we can use the built-in authoring system to create a tour through this data. So let's go ahead and type in quakes here as the name of our tour. And we'll start out fairly far from Earth. and we'll go ahead and set this up as a time series. And we'll start out at the beginning of the time series range here, and we'll add a new slide. So the way that slides work is sort of like PowerPoint, except you have the universe as your backdrop. So you set up whatever data layers you want, you turn them on and off, you set their opacities, and then you basically create views on them. So we started out with one view, and then we'll move in, and then tilt our camera, and zoom in here, and then we'll right-click on our flag, our slide here, and we'll set the end camera position. But before we do, we'll move up in time. And so now we'll set the end camera position both in space and time. And then when we go about playing this, you can watch that all these earthquakes are actually firing off over time as we're coming in and zooming in on this. So by putting together, stringing together several slides with different data, you can bring in shapes, text overlays. We can insert, for instance, the date here and the time, and go ahead and save that here. Let's go ahead and make it a larger date and time. And we'll go ahead and put this here. So now when we play this back, you can actually see the date and time as you're going through. And by putting in these metadates and metatimes, it'll actually turn the text into something that actually has a live data based upon how time and space changes. So you can put things in like the current latitude of and longitude of the focus point, what the zoom level or altitude level is, things like this date and time or other types of data values. Also, as I was mentioning, there's being able to actually select and hover over data, and we can hover over that, and you notice the date and time that we had selected for the hover value. You can actually inspect any data points you want, and it shows you all of the columns for that particular row that you've then selected on the side, so you can have a two-way link to this. And they'll also be demonstrating how this can be taken all the way out into Excel, so you can actually look at individual rows in Excel and then bring it back to WorldWide Telescope. At this point, that tour could also be annotated with other sorts of drawings, text, pictures. You could have a music soundtrack, a audio overlay for it to do more explanation of this. You can also, besides having things inside the Earth, you can have things in the atmosphere. You can have motion vectors. You can have 3D models of things. You can also bring in orbits. So a lot of times data will be collected through satellites, and you'll want to have the ability to visualize satellite data as well. So, for instance, this is a quick tour created with, this is most of the operating satellites today, a combination of low Earth and geosynchronous orbits. I'm sorry, actually this is a small subset of currently operating ones. One of the things I've had to do when we're visualizing space-based information is that if I put up an entire download of all the data that NORAD's tracking right now, you can't see a single pixel of Earth through it. If you make them even, the slightly opaque, essentially, and have any sort of trail to its orbit, it essentially, there's so much space trash up there right now that you cannot see so we're not just polluting. I thought I already got the 15 minutes.
Yeah, that was a premature 15 minutes. This is accurate.
Okay. Unfortunately, the premature 15 minutes, I kind of sped up my my program to do that. So I may be finishing a little bit earlier.
Okay, Q&A is good too.
So, as we're, I'll take a point right now and start getting some questions in. and responding the rest of the tour towards Q&A. Yes?
Is it possible or how possible to take this tour to save it somehow to send to somebody else so he would look in the same data along with pictures and everything else?
Right. So that's the entire purpose of the tour. This is a publishing. So the question was, is it possible to save the tour and all the data and the pictures and everything and send it to someone else? And that's the entire purpose of the tour. The idea is that you wrap up in the tour the narrative, the data, the contextual exploration tools. You put it all together in that package and you send it to someone else. And since this is a free tool, then they can install the package, or in some cases they can use the web version of it, and they can view that tour. They can experience your slide-based narrative to start with, and then at any point they can stop. And because these tours are not videos, they are actually, at any point you can stop and explore anywhere inside that data. And you can look at the individual data. So the downside of this is that you can't show your data and hide it at the same time. Since it's meant to be open, the whole idea is as you ship this to it, they get all the data that was used to visualize it. Not necessarily to produce it, because if you've done some pipeline steps to reduce the data before it is imported into WorldWide Telescope, they won't see that part of it. So that's something you should also document and make open in another mechanism. Does that answer your question?
Yeah. I actually want to be more specific. Like, what kind of format? How does it? I actually meant to be more specific. Like, what kind of format it uses? Like, for example, if it's Excel, it zips everything together in one file. I know Earth is using WTML, but you can put that in WTML. So how does it?
Okay.
I mean,
so the data itself for things like spreadsheets are actually stored in a CSV, tab delimited TDF CSV type format internally. And when you're in the product, if you don't have, if you have Excel, you can use our Excel plugin and immediately take any layer and visualize it as a spreadsheet and see it with all of the settings using our Excel plugin. Because you can also cut and paste that layer directly into any type of column tool. So if you have a database tool that you can cut and paste into SQL or Microsoft Access or Excel or any type of tool that understands a tabular format, you can even paste it into Notepad if you want. I mean, but obviously tools that know how to deal with columnar data. Now the interesting thing is you noticed I had created this shapes, this false. I'd loaded this false, and that was a shape file. Okay, but what if I want to get that data out? Maybe I don't know how to deal with a shape file. But if I actually copy that in and paste it into Excel, I actually have never tried this before with this particular file, so we'll see if how well it works. So there we go. That is OGC well-known text and suitable for ingesting into SQL Server right there. So it turned it from a shape file that you would have to have, you loaded it as a shape file, and now you can actually take that data and cut and paste it into Excel and use it as well-known text. And then you could actually decorate it and look at each of the values individually, put it into SQL Spatial, or do other types of things with it as well. So we try to make it so that the data that goes in there, there are a few things like 3D models that we have in 3DS format that we don't turn into text because there's really, not a good representation of it. We may eventually go with sort of an XML model representation that's compatible with industry standards. But right now it's more than most scientists want to deal with as text. So we do have ways of getting data in and out. Now the other important aspect to this is that we have a few different APIs to work on processing data and getting data in and out of WorldWide Telescope. So for our web version, we have a JavaScript web script. And let me go ahead and quickly pop off to the WorldWide Telescope web control. So I showed you a little bit of a view of the features of like the sky and the Earth features. Now, the web view currently, it doesn't have the scale and all the capabilities of the desktop version because we don't have GPU support. We're hoping that over time that technology will advance enough that we'll be able to provide that sort of thing inside the web browser. But at this point, we don't have a date or time when that will happen. But in the meanwhile, for our original astronomy, for our astronomers, we actually gave a pretty compelling web view. Remember, I zoomed into the California Nebula, and we were able to zoom in and take a look at that. If I didn't tell you otherwise, you might notice a slight lag in the frame rate between the web version, but this looks almost identical to our full desktop product, right? And if I go over here into Cassiopeia, I can also do that same sort of setup here where I can set a foreground image of the X-ray. And let's go in and guess what? We can see that same X-ray image for the nebula that we saw earlier. And crossfade back in, and here we go. So there's a lot of the same functionality for certain modes. Now the 3D solar system mode, for instance, being able to fly out to the large-scale structure of the universe, unfortunately, that's something that's really not there. And also showing 50,000, 100,000, 1 million data points and doing time value on that without the GPU support, that's not going to happen in the web version. But you can do a limited amount of data where you're showing a subset of the data in the web version and plot that fairly quickly as well. But now we say we have a lot of power in the desktop application. How do we get your data into that if your data involves connecting up to a large database and has a lot of application code that's using your particular types of management methods of that data? So we have what we call our loosely coupled API that is basically we expose a web server in WorldWide Telescope that then you can, from JavaScript, Python, C#, whatever language you want to connect to it. If you can instantiate a web client from your application, you can do a connection to WorldWide Telescope and actually send data, send control, move things around, put data in, turn layers on and off, and do all sorts of management of the whole scheme of all of this data visualization in such a way that your application can basically have its own visualization window into all of this, and then can actually save these tours that you create in that format for other people to consume. And so we're going to be showing you how to actually get started with working with that, and we call that the LC API.
More questions?
Yeah.
When you were importing the shapefile, it occurred to me that you might be thinking about engaging in an effort to develop wizard plugins to Excel that would expand beyond importing a tab delimited or comma space separated file, but actually say, is this imported data set a shapefile, or is it a WFS file, or some other well-recognized formats? Are you thinking of putting any effort into that?
So right now, our plugin for Excel doesn't actually deal with taking OGC files directly into Excel and turning them into columns and tables. You have to import those directly into WorldWide Telescope, and where we can directly translate into a fully textual field in Excel columns, we do. But there are some types of OGC formats that just don't translate very well into simple column and shapes. Shapefile is one that there's I could find almost a perfect mapping between well-known text and shapefiles. It's almost XSLT if shapefiles were in XML2. But we have to basically convert them into XML with just a fairly simple pattern. But there are other types of OGC that don't translate so well, that have much more complicated organizational hierarchies, and so they're not as easily translated into something that you would work with in Excel. But because of well-known text being supported directly, there's a lot you can do with geometry and geography as part of your SQL and Excel tables and such.
Question here and then later.
I have a question related to social collaboration of researchers while working on a particular data set, a particular concept of astronomy itself. Like there is a Microsoft Research called Research Workbench, which they do with respect to literatures and all the stuff. Similarly, is there something that you're planning on getting a social collaboration in this where they don't have to use the local resources, but they can use the cloud resources on the back end with the GPUs, but they can interact with a specific data set they're looking at between two different collaborators. He's giving access to them, so you can look at it and then interact between them immediately without activate all these local resources or anything like that.
So we do have this concept of community plugin, and that's been available since our day one. But what it is an infrastructure where you create WTML, which is our markup language. It's an XML extension that allows you to set up. So, for instance, when I was browsing here, you notice that there's all this data that's available, and some of these are catalogs, some of these are images, and there are various types of data that we have. You can have web links, you can have web applications that you click on one of these and it pops up a web application, and these can pop up things that are embedded. But with a community, once you actually join a community, it's the database for that community, the security profile of that community. So it essentially allows you to extend the data world of WorldWide Telescope by wiring up your own community into it. We've contemplated the idea of hosting our own communities. We originally, when we started up, we wanted to decide whether we wanted to actually have a YouTube-style submission where everyone would throw stuff up. And one of the things that we decided early on is that because we wanted some sort of a peer review process for publishing, so we decided that on our tours that we publish, we have sort of a committee of scientists who review these tours and help decide what's put in terms of external submissions. But we also decided we needed a way to open it up, and so we have this way that people can create their own communities. But it requires a lot of programming on the current version. We're considering opening it up to more of a cloud-based service that you can use, but we haven't announced anything on that. But your feedback in terms of how useful that would be to have something that would basically be a push-button ready to go versus having to do coding, and whether that would help jumpstart people. Initially we were concerned that the YouTube style format of letting people just share data willy-nilly without peer review would lead to exactly the same sort of crap you get all over YouTube, with Planet X found in WorldWide Telescope and things like that.
Yeah, I have a question regarding massive four-dimensional data sets. You mentioned that for this model output, for example, we have some research on atmospheric models and the output net CDF data. That is to decouple the atmosphere into real four-dimensional in a raster fashion, which means the entire atmosphere is divided into cells in 3D space and also in time. So I have the question about is any plan for WorldWide Telescope, or what's your comment on how to visualize that kind of data in both 3D space and the time?
So what I will do is actually leave that one up to Rob, because he's coming on next and he's going to start into that. And at this point, he will have a lot of discussion and drilling into exactly those sort of questions. So I'll leave that to him, and
5-minute break while we swap.
yeah, we're going to have a 5-minute break.
Oh, I'm sorry, one more question.
Okay. I have a question about the level of detail, the LOD part.
Yeah.
In your example, you showed that you actually wrote the image about 1 terabytes, right?
We had a one terapixel image, yeah.
Yeah.
But that's the largest fully seamless image. But our Earth data, which is much of it shared with the Bing Maps team, is over a petabyte of data as well. So it's the scale of data for the Earth is significantly higher than astronomy, but it's not 100% coverage at the same pixel arc second per pixel level.
My question is that when you zoom in or zoom out, you actually wrote different levels of data dynamically, or you have resampled those data into different resolution levels?
Okay, so what we're actually doing in that is that we pre-process the data into a tiled multi-resolution pyramid, and then we load the particular tiles that are most interesting for the area that's affected. So we have a very novel voting strategy that basically always gets the best coverage quickly, and then as you're moving and finally stop and look at someplace, we refine it until you get the highest level detail on that. But we use a relatively we can use high latency, low bandwidth connections very profitably and still get a pretty good experience with that, along with our caching techniques. So it's a very good performing technique, and but it requires pre-processing into a tiled multi-resolution pyramid. The storage cost of that is approximately a 1.3 ratio from the original data. But the difference in terms of performance of access is orders of magnitude versus having to access the data and resample it. Okay, I better hand off to Rob now.
So, and one other thing, while you guys are here and Jonathan's here and stuff, while you're thinking about your data sets and what you want to visualize, one of the things we'd like feedback on as well is what sorts of primitives for the visualization side would you like to see and at what level? So while you're here, there's a bunch of stuff we can do on the Earth side, but we want to also understand what it is you'd like to see, and that'll help us as well.
And we want to play with real data over the next couple of days and actually bring in your thing, because we're showing examples of some of the collaborations that we've done in the past, but we want to really make it about what your data is. So here's Rob.
So you have 2 days to think of that and provide us with your feedback. And before I get to you, I want to say that we do have a free tool that goes with this to process the tiles, to help you to create different levels of tiles if you have images. So that's downloadable from RMC.